This is a lesson on the introduction to common logarithms. Common logarithms have come up before in the discussions on logarithms as a whole, but now we're going to concentrate on common logarithms and their uses and in applications, etc. So first off, common logarithms are base 10 logarithms, and base 10 logarithms do not have to write the base. So anytime you see the log of, for example, 50 with no base given, it's understood that that's base 10. And they're meaningful for us because we can now solve previously unsolvable exponential equations and then also applications. And they are programmed in your calculator, so your base 10 logarithms typically will be solved on your calculator, unlike most of the other ones. And this is important too because when we start graphing log functions, we couldn't graph base 2 logarithms before. With common logarithms, if you do it properly, you can graph those even for other bases, so that's helpful. So to begin, let's evaluate the following, correct to the nearest tenth. If you had, let's say, the log of 100, so that is clearly base 10, if you want to use your calculator, all you do is you go log and then 100. Now the bracket, of course, will open up and you just have to make sure you close it. In fact, as long as that's the only term you're using, you won't even need to close it. And you'll get 2.0. Now this was an easy one. You didn't even need a calculator because 100 can be expressed with a base of 10. So if you solve this the old way, that is, you thought 10 to what exponent is equal to 100, then by getting that common base of 10, you will get y is equal to 2.0. So you get the same answer. And notice I'm writing this to the nearest tenth. So that one wasn't required, but if you did get something like this, the log of 537, well, this one you don't have that choice because you cannot write 537 with a base of 10. So your only choice is to use your calculator, really. So you just entered in log 537 and you should get to the nearest tenth 2.7. It's like 2.7299. So it comes in handy, not so much for this type of problem, but for exponential equations. If you think way back to when we were looking at exponential equations, we were able to solve them by getting a common base. But as we saw with this previous example, you can't always get a common base. So these we will solve now, stuff like 3 to the x is equal to 20. And 3 to the x and equal to 20, you cannot get a common base for 3 and 20. So we're shut down. 27 can be expressed with the base of 3, 9 can, 81 can, but not 20. So this is where common logarithms come into play. And what we do is we take the log of both sides. And by that I mean we just take the log of 3x, write the log of 3x is equal to the log of 20. And that doesn't look any better, but if you apply the power law, you might recall that an exponent within the logarithm can be taken to the front and multiplied. And that's what we want, because now we've got the x, the variable, out of the exponent, and we have it isolated. And just do a little bit of simple algebra on it through division, divide both sides by log 3, and that's what you get. So x is equal to the log of 20 divided by the log of 3. Now I didn't need the brackets when I wrote it like this, but if you did want to solve this on your calculator, you will have to put the bracket up, at least the bracket around the 20. So log 20 divided by log 3 will give you 2.73. The instructions were to round it to the nearest 100th. And that's basically the method. Now, you even if you could get a common base, you can always do this, but you should still be looking for common bases if you can. Now, number 2, 15 is equal to 2 times 5 to the x. This is more complicated, and I'll work this one out by hand. Before you get too carried away, I would recommend that you divide by 2. Some people won't do this. There is a choice. But the normal method, even when we are dealing with common base type problems, the normal method was to get one power equal to the other. So you always try to strip it down as much as possible. So 15 divided by 2 is 7.5, and now we take the log of 7.5 and write that as the log equal to the log of 5 to the exponent of x. And then when you apply the power law to the right side, you'll get x log 5 is equal to log 7.5. And then divide out both sides by log 5, and log of 7.5, close that bracket, divided by the log of 5. And then we get an answer. So I'm getting x is equal to 1.25 to the nearest 100th. So very useful. Next one, a little different. In fact, this question probably should have said evaluate instead of solve, because it is not an exponential equation yet. But remember, when you're dealing with questions like this, the log of a number to a base, really what you're doing is you're thinking 3 to some exponent is equal to 8. And because we cannot get a common base between 3 and 8, we take the log of both sides. So we write this as log of 3 to the y is equal to the log of 8. Take the y to the front by applying the power law. So y log 3 is equal to the log of 8. And therefore y is equal to log 8 divided by log of 3. And then you just go right through with it. And to the nearest 100th, we will get 1.89, which actually makes sense because we would think 3 to the exponent of 2 would be 9, so we should be just a little bit short of that. Let's try another one. 4 to the x plus 1 is equal to 9. Now these questions get interesting when we get situations like this where we have a binomial in the exponent. We do the same thing. We take the log of both sides, so we get the log of 4 to the exponent of x plus 1 is equal to the log of 9. Apply the power rule, and that x plus 1 comes to the front. And what you need to remember is that we have to have a bracket around it because it's being multiplied by the log of 4, both terms of it. So the entire exponent. Now I know that some of you are thinking that the easiest way to solve this is now to divide by log 4, and you can. And I'm going to show this to you two ways, and then I'm going to indicate which is the preferred method. If you divide both sides by log 4, you get this. So therefore x is equal to the log of 9 divided by the log of 4 minus 1. And that works. And you will then get that x is equal to 0.58 to the nearest 100th. And while that works, this is recommended. And this is recommended because when the questions get more complicated, this works better. And I'm just going to check in right at this stage. X plus 1 log 4 is equal to log 9. And this is a straight algebraic method. We take that log 4 and we distribute it in to both terms. So we then get x log 4 plus 1 log 4 is equal to log 9. And then you just isolate the variable. So x log 4 is equal to the log of 9 minus the log of 4. And then you finally divide by log 4. Now I know this is looking like a lot of work, but it does pay off on the more complicated questions. And then divide by log 4. And on your calculator, you've got to be very careful. Most people will open a bracket and then go log 9, close the little bracket, minus log 4, open, close, around the 4, close the big one, and then divide it by log 4. And of course you get the same answer, or you should get the same answer. Do not make the mistake of trying to cancel those log 4s. When you have log 9 minus log 4 divided by log 4, don't just divide out the log 4. You can't, because that log 4 belongs to both terms on the numerator. Just by looking at the two, the first one looks better, but as you'll see in the next example, you're better off doing the algebraic one when they get more complicated. Because here we have two binomials in the exponents. So we're going to get the log of 3 to the x minus 1. We cannot get a common base, and that's equal to the log of 8 to the 6 minus 5x. And then when you take the log of both sides, or excuse me, then when you apply the power law, you'll get x minus 1 in brackets times the log of 3 is equal to 6 minus 5x log 8. And here, if you did try to use that simpler method just by trying to divide by log 3, it won't really get you anywhere, because then you have to deal with that log 8. So it is better to distribute the log 3 in. So x log 3 minus 1 log 3 is equal to 6 log 8 minus 5x log 8. And this isn't looking very good, but if you gather your x terms together on one side of the equation, then you can solve this problem. So take that minus 5 log x, bring it to the left side. So we get x log 3 plus 5x log 8 is equal to 6 log 8, so it stays where it is, plus log 3. And then we get the x out of those two terms by factoring it out. So we factor out the x. So the x comes out and divide it from both, and we get log 3 plus 5 log 8 is equal to 6 log 8 plus log 3. And then x will be equal to, you divide by that binomial log 3 plus 5 log 8. So we get 6 log 8 plus log 3 divided by log 3 plus 5 log 8. And then on your calculator, be really careful with it. Open up a bracket and go 6 log, open close around the 8, plus log, open close around the 3, and then divided by open log 3 plus 5 log 8. Open, close, and then close the big one. Now, a lot of the questions you're going to see like this will simply write them as in the algebraic form. So they'll keep it in that state, that form. 6 log 8 plus log 3 divided by log 3 plus 5 log 8. So you should then get 1.18 for this one. Let's take a look at one more example. Now this is more complicated because we have two x terms, but we also have this loose factor of 5. And we cannot divide by 5 from both sides. So we have to take the log of both. So this becomes the log of 5 times 3 to the x is equal to the log of 10 to the x plus 1. And our only choice now is to break up the logarithm. So you recall perhaps us doing that a few lessons ago. So break up the logarithm. And by that I mean we're multiplying as a single logarithm 5 times 3 to the x. So using the product rule, we can break that into the log of 5 plus the log of 3 to the x is equal to the log of 10 to the x plus 1. So therefore we get log 5. Use the power law to get the x's out, plus x log 3 is equal to x plus 1 log 10. Now if you're right on top of this one, you might recall that log 10 is equal to 1, so our equation would even be simpler. I'm not going to do that. I'm going to deal with this as though it was just a regular question. But if you were really sharp on this, you might have seen that. So I'll distribute that through. And then all you do is you get the x terms together wherever they are. I'll bring them to the left, and I'll write this as x log 3 minus x log 10 is equal to log 10 minus the log of 5. Factor out the x, and you get log 3 minus log 10 is equal to log 10 minus log 5. Then finally, through division, we'll get log 10 minus log 5, all divided by log 3 minus log 10. So make sure you get those brackets put up. So on your calculator, little brackets around the 10, around the 5, around the 3, around the 10, and then big brackets around the outer. And you should then get x is equal to negative 0.575. So x is equal to negative 0.58. Now this is the algebraic method to solve these. However, you do have the choice, if you wanted, you can solve these on the calculator. Now this is not new. You've done this with every other unit. But if you took a look at the last question, example number 6, and here we have it again, 5 times 3 to the x equal 10 to the x. Enter y1 is equal to 5 times 3 to the x. And then enter y2 is equal to 10 to the exponent of x plus 1. And then on your calculator, adjust your window setting. Probably just your Zoom 6 standard would be adequate. And you will get a graph looking somewhat like this. Now yours maybe isn't as clean looking as mine, but it'll do. I adjusted my window setting on this to get a really good looking graph. Y1 is the first one, Y2 in black is the second. And as we've always done with this sort of equation, when you're solving them, where you've got both sides of the equal sign graphed, we just use the intersect key to find out the intersection of the two, where they meet. And there you will get x equal negative 0.58. I won't take up your time to do that, but it does work out. So if your algebra fails you, do not hesitate to use your calculator. Thank you for your time.